Hey guys, welcome back to another video. In this video of electrochemistry, we're going to be deriving the Avogadro's constant and the Faraday's constant. Now, in case of Avogadro's constant, you probably already know what it means. So if I give you an example, 1 mole of any compound, any element will contain 6.02 into 10 to the power 23 atoms of that element. So if I say I have 1 mole of Na, 1 mole of sodium that is, therefore 1 mole of sodium will have 6.02 into 10 to the power 23 atoms of Na. Therefore, a mole is a measure of how many atoms of that element compound molecule there is, right? Therefore, a mole is a measure of any amount. Now, this 1 mole can be broken down into 6.02 10 to the power 23 atoms. So this amount can be anything. So it can be that 1 mole of water has 6.02 into 10 to the power 23 atoms, or it could be, let's say, 1 mole of, 1 mole of phones. 1 mole of phones would have 6.02 into 10 to the power 23 phones, right? So 1 mole is basically a measure of how many of that individual particle there are, right? So we're going to derive how the number 6.02 into 10 to the power 23 is derived, right? Now, in doing so, we will also derive the Faraday's constant. Now, Avogadro's constant, you already know what it is. So I'll explain what Faraday's constant is. Now, the Faraday's constant is telling you the amount of charge in 1 mole of electron, right? So if I have, let's say, one individual electron, then I know the charge on it. If you look at the data booklet, you know the charge on 1 electron is 1.6 into 10 to the power minus 19 coulombs of charge. However, what is the charge on 1 mole of electron, right? 1 mole of electron will have 6.02 into 10 to the power 23 times 1.6 into 10 to the power minus 19 coulombs of charge, because 1 mole of electron will have how many electrons? 6.02 into 10 to the power 23. That is Avogadro's constant times the charge of individual electrons. So the constant, the Faraday's constant, turns out to be 96500. And all of these things we're going to be deriving the Avogadro's constant and the Faraday's constant using electrochemistry. So let's see how we can do that. So the principle of this derivation is based on the Avogadro's constant being given by the charge on 1 mole of electron divided by charge on 1 electron. I'll divide 1 mole of electron, that is charge on 1 mole of electron, charge on 1 mole of electron divided by what? Divided by the charge on 1 electron, that is E. If I divide the charge of 1 mole of electron by the charge on 1 specific electron, 1 individual electron, I'll get the amount of electrons that there are in 1 mole of electron. So I'll derive how many electrons make up 1 mole of electron. Now, in our case, we know Avogadro's constant is 6.02 into 10 to the power 23. However, we have to derive that from somewhere, right? So this process is a way to find that Avogadro's constant, right? So how do we do that? I basically made up an example. So let's see with that example how step by step we can derive the Avogadro's constant. Now, first up, we're taking an example of silver being produced at the cathode, right? So what do you know about cathode? What happens at the cathode? You know, reduction takes place, right? So let's say there was a solution. This is your cathode, right? There is a solution of silver ions, Ag2+. sorry, Ag plus ion. And these ions would go to the electrode, gain electrons, and be discharged, forming silver on the electrode, right? So there will be some amount of silver being deposited on the surface of the electrode. Now, let's see how we can derive the what you call it, Avogadro's constant from all of these information, right? So the question is telling you electrolysis is being carried out of silver chloride and 0.28 grams of silver is being deposited at the cathode. So at the cathode, how many grams of silver is being deposited? It was measured to be 0.28 grams. Fair enough. Now for this to happen, you must have passed some amount of electricity, because in this case you are discharging the silver ions, you're providing a flow of electrons, right? You're providing a flow of electrons such that there is a bunch of electrons ready to discharge your silver ion, right? So, oh, by the way, this is not an electrochemical cell. This is electrolysis between AgCl. So you're passing some amount of current between two electrodes. That is, there's a cell which is providing the current, which is able to provide the electrons to the silver ions such that it can discharge the silver ions, right? So there is a cell over here. I mean, there is a battery or, direct current supply, which is being able to discharge the ions. Okay, fair enough. So the important information to us, 0.28 grams of silver being deposited. And to do that, it was measured that 0.501 amps was provided. So 0.501 amps of current was provided for 500 seconds to discharge the silver ions and produce 0.28 grams of silver atom on the electrode surface, right? So the question is asking you, prove the Faraday's constant from this information, right? After we prove the Faraday's constant, we'll be able to prove Avogadro's constant using this formula. Okay, fair enough. So first, let's derive the Faraday's constant. So what we're going to do at the beginning is we're going to find the moles of silver produced at the electrode, right? Okay, so we know the mass that is produced divided by the molar mass of silver, that is 107.9. So the moles turn out to be 0.0026 moles. Great. Now form an equation for what is happening at the cathode. That is the half equation. So 1 mole of silver ion is going to gain 1 mole of electron to produce 1 mole of silver atom, right? Now, using the ratio, I can figure out that 1 mole of silver atom is produced when 1 mole of electron is given to 1 mole of silver ion. Okay, fair enough. Therefore, if 0.0026 moles of silver was produced, there must have been 0.0026 moles of electron, because you're producing, note, 0.0026 mole of silver atoms. Therefore, how many moles of electron do you need? The same amount, because the ratio is 1:1. Fair enough. Okay. Now, granted, you know this amount of information about the electrons. This is the crucial information. Fair enough. So, you know 0.0026 moles of electrons were needed. Now, keep that in mind while we calculate the amount of charge that was given by the cell or by the direct current. So, how long did we pass electricity? 500 seconds, right? It was given in the question. So within 500 seconds, 0.0026 moles of electrons were transferred. So first, let's find out the amount of charge that was transferred, right? How do you find that out? You know I is equals to Q by T. Therefore, the total amount of charge will be given by current times how long the electricity was there, right? Fair enough. So you know the current, which was given to you in the question, which was 0.5018 amps of current. For how long did you carry out the electrolysis? 500 seconds. So how much of a charge did you provide? 250.9 coulombs of charge you provided. Fair enough. So remember, the amount of, or the moles of electrons that got transferred were 0.0026 moles. Therefore, we can conclude that to transfer 0.0026 mole of electron, we needed 250.9 coulombs of charge, right? Therefore, to transfer 1 mole of electron, how much charge would we need? Divide either side by 0.0026, 0.0026, and you're going to find out the charge that would be transferred, or the charge carried by 1 mole of electron. So this is your charge when 1 mole of electrons are transferred, right? So this is the Faraday's constant. That is, 1 mole of electron will have 96,500 coulombs of charge. So this is how we find out the Faraday's constant. Now, mind you, an important note is I made up this question, which is why you get the accurate answer, that is 96,500. But in the question paper, you may not get the exact amount of Faraday's constant. You may get something like, let's say, 97,800 coulombs. But that is all right. That is absolutely all right. And in the MS, you'll see this is the exact answer. So don't, be worried, or don't change anything in your answer to make sure that your answer is the exact same as 96,500. They always, somewhat change the data to make to give you, a Faraday's constant that may be a bit deviated from the real amount, right? So in your question paper, the answer you get might be a bit different, but that is all right. Okay, so the real Faraday's constant is 96,500 as well, just as you found out in our case. However, again, in the QP, if your answer is different, that is all right. I mean, it shouldn't be abnormally different, like, 200,000. So in that case, you'll know your answer is wrong. But yeah, that's how we figure out the Faraday's constant. Now, using that information, we can find out the Avogadro's constant, right? How do we do that? The same equation, right? You divide the charge on 1 mole of electron, that is 96500, divided by the charge on one individual electron, such that you will find out how many electrons there are in 1 mole of electron to give you the exact 96,500 coulombs of charge. Okay, fair enough. So you'll divide 96,500 by the charge on 1 electron that is given to you in the data booklet, and you'll find the Avogadro's constant. In our case, the value we get is 6.03 into 10 to the power 23. The real Avogadro's constant is 6.02 into 10 to the power 23, which is all right. Even in case of your, derivation of Avogadro's constant, your answer might be slightly deviated, but that's nothing to worry about. That is going to happen if your answer in the previous step is slightly inaccurate. And in your question paper, it might just so happen that your final answers may be a bit different in comparison to the real data. Okay, so that's all right. Now, this is how you find out the Avogadro's constant. Divide the charge on 1 mole of electron by the charge on one individual electron, right? Fair enough. Now, one thing I'll also answer is, you may ask, fair enough, I found out the charge on 1 mole of electron, but how can we derive the charge on one specific electron? So I just took this data from the data booklet, but you may argue, how did we find this, this constant? The answer is, we don't derive this constant. It was experimentally figured out. That is, I guess the name of the experiment is oil drop experiment or something.
Yeah.
And if you are interested, you can search it up and see how it's actually derived. I mean, it's not derived. Bunch of experiments were carried out to accurately determine the charge on one individual electron, right? So this doesn't have any derivation, as far as I know at least. This is a given. And this, you do derive the Faraday's constant. And once you do so, you will be able to find the Avogadro's constant. So, oh, by the way, this denotes Avogadro's constant, apparently. So yeah, that is it for this video. So in this video, we learn how to derive Faraday's constant, and using that, how can we derive Avogadro's constant, right? So this is it for this video, and see you in the next one.